So the first group is Thermo-Chemical, short. The group has two chairs, Ed Canero from Arizona State and Greg Hirth from Brown. They both couldn't be here, so they asked me to take to present one of their talks. There are group members. That's me, yeah. Group members are Colleen Dalton, who also gave a talk today, a 50-minute talk, and then Marie Long, but she can't make it either because she just had a baby. What can I say? I can't remember. I put my slides together just very recently, so I can't really remember what I have. I'll choose it. There you go. Any other talks on this thing? Yeah. Okay. Right. So. There we go, right on. So from discussions within our group, we have basically identified the following themes that are as Anne mentioned, drawn from the Grand Challenges document, which are listed here, and we'll present those themes later on when we start the forum. So you don't have to read all this information, but I'll put all these themes together with the other groups as well before we start the forum. So let me go straight to what I want to talk about, and that's together with Colleen, we're going to talk about thermochemical processes and structure of the mantle, and I'll give an example from the lower mantle and highlight those themes using a specific example, and that is of the imaging of mantle plumes. And then following me, Colleen will follow me with a talk about upper mantle seismological results and grand challenges. Right. So I'll talk about plumes, and I'll use that as an example of a long-standing science challenge, and highlight the questions that we identified as questions for the next 5 to 10 years. So here are 3 cartoons. If you don't know what plumes are, I think we are now going back to the 1977 view of the mantle with large, low shear velocity provinces and subducting slabs that pound on that thing and erupt plumes. The reason I use plumes as an example is it is actually identified by the group as an issue in understanding the style of convection in the mantle, specifically addressing the origin of hotspot volcanism on the Earth's surface and the nature of the lowermost mantle, the thermochemical nature of the lowermost mantle. Okay, so the results for many years of seismological research is put in this graph. We have a lot of seismological images of the mantle that indicate reduced shear velocity or compressional wave velocity structures across the mantle, and some of these structures extend well below, for example, how deep ridges go. So they must have an origin that is not passive ridge dwelling, but they really are connected to deeper mantle processes. So the question is, what are these things? Are they plumes, and do they actually match our geophysical expectations for plumes? So if we look at these things, do the scales and the amplitudes of these low velocity structures, are they consistent with what we think about what they should be for plume upwelling, for thermal plume upwelling? Are they rooted in D-double prime? Why are they tilted in some cases? Is that also is that consistent with geodynamics of the mantle? And how do they interact with the transition zone? So these are really the themes of the research. To go beyond understanding these structures, or to go understanding these structures and interpret them, I listed here the things that we need, the things that are the next steps. And I put there new data, and that's not simply just recording the same old as we've done for the last 30 years, but it's really finding mechanisms of seeing the much smaller scale heterogeneity in the mantle. So far we've only seen the red spectrum of heterogeneity. We can also use the seismological data that we have today by being much more clever about utilizing all the information that is between P, S, SKS, and etc. So there are a lot more signals contained in seismograms that we have yet to explore. The second theme is, or second issue is the interpretation of both the data and the images that we're producing from the seismological data. Do it with proper data and model resolution analysis, and interpret the images with the proper physics. And that will require collaboration with other communities. So first off, new data, and something that we emphasize in our group, and that's also will be emphasized by other groups, is coverage of the seismic networks on the globe. So far, we mostly have our seismological stations on continents or on islands. We have yet to cover in a comprehensive manner the oceans. Here are two images from both, from left is from an oceanic setting from Hawaii, and on the right is from a continental setting. This is the Yellowstone plume images. And they clearly show that having arrays, having small wide aperture but small density or high density arrays, that is the way to see deeper into the mantle. This is the way to go and see the plume stems or sea stems or upwellings coming from very deep. Another example of that, of the complexity that you can see in plumes, is seen in transition zone images. This is an example from the Africa array on top, from Andy Nyblade, and on the bottom from MIT group. And they're showing that you can actually see transition zone deflections and undulations, not always directly beneath the hotspot, but some of these undulations are offset from the plume, and telling us that some of the dynamics of the plume upwelling is not simply showing a vertical, a rapidly rising plume. So plumes on the, networks that we would like to see being developed are networks on the ocean seafloor, like the one that's used to make the plume image of Hawaii. And on the right is an image of the plume array that involved ocean bottom seismometers in the Pacific. So these are seismometers on the seafloor. There are ideas also to put seismometers within the water column itself, and these are ocean floats. And there's an entire SIG meeting on this tomorrow. And if we could attain coverage that was given here on the left from the Argo website, we could actually make incredible progress in our seismological imaging. In terms of looking at all the data, we can actually explore a lot more signal that is contained in seismograms. And so this is an example from Andreas Fichtner's work, who uses full waveforms in tomographic inversions. This is on a regional scale, and this is focused on Iceland. And you're seeing here on the bottom panel the complexity of the Icelandic plume, suggesting that plume upwelling, if this is indeed a plume, that plume upwelling is not necessarily involving a vertical conduit. It will involve 3D seismology, so 3D methods, proper 3D kernel calculations, the 3D forward problem, and that will require high-performance computing. That was inverse methods. There are also forward modeling methods. This is an example from Rickers et al., who use signals that are coming in the coda of the P wave. And so by looking at the small diffraction signals of the P waves that are following the direct P arrival, you can actually do a better job of imaging structures deeper into the mantle. So the panel on the right illustrates to you that you can actually get a better an image, resolve better resolve better the plume stem in the lower mantle if you're using the additional waveform that is following the main arrivals, such as PNS. The third thing about better data new data is better interpretations. And so when we're looking at when we're looking at seismological images, we have to wonder, or we have to consider what whether they're consistent with the physics of the process that you're studying. So for plumes, we have to, for example, consider how geodynamics and how mineral physics expects plumes to look like, how they predict plumes to look like. So on the bottom is a panel from a paper by Stiles et al. That's based on an earlier paper by Lin and Van Keken that computes the seismological expression of plumes given a rheological structure of the mantle, given a relationship between pressure, temperature, and composition with the seismic wave speeds. Better interpretation also means a more careful analysis of the seismological images in terms of how they relate to expected images from, say, geodynamics and mineral physics. So this panel here shows a computation of seismic wave speeds on the left, a predicted set of seismic wave speeds on the left, with one that is expected to be seen by tomography. So a full analysis of the resolution of seismology is necessary to interpret the images. And lastly, you can look at, in a forward modeling sense, see how expected plume structures in the mantle produce seismic waveforms. And so this is an example of calculating the waveforms for a structure, for a mantle with a plume, and seeing what sort of perturbations, what sort of data this particular model will produce. And then we can ask ourselves the question whether the data that we predict, or whether the signal that we predict from the geophysical plumes that we put into the model are actually useful data for our imaging. Okay. So this is what my contribution. Colleen will follow next, and then these are again the main themes, the sort of the summary of the main themes that we'll put up again before we start the forum. But I'll ask Colleen now to talk about the upper mantle.
Well, good morning. As Jeroen has mentioned, the theme of our committee is thermochemical internal dynamics and volatile distribution. And of the 10 grand challenges, there are 5 that bear directly on this theme. Where are water and hydrocarbons beneath the surface? How do magmas ascend and erupt? Where is the lithosphere-asthenosphere boundary? How do temperature and composition control mantle convection? And how are Earth's internal boundaries affected by dynamics? So it's obviously not possible today in the time that I have available to delve into each of these topics in detail. And so our committee has identified 3 scientific themes and 3 key directions for the future to focus on for today. So of the 3 scientific themes, 2 of them involve the lithosphere and the asthenosphere and the interactions between those 2. And the 3rd one concerns our ability to distinguish melt, volatiles, temperature, and composition from seismic images. For the future directions, we've tried to classify the outstanding challenges into 3 rather broad and simple categories. The first one, improving seismic images. So this includes new analysis of existing data and also through collection and analysis of new data. And for the new analysis of existing data, we're talking about things like utilizing more of the waveform or the full waveform, integrating different measurement types into an inversion, and high-performance computing as a few examples. The second challenge is to improve interpretations of seismic images, and this, of course, is through collection of new experimental data, which really is what informs our knowledge of how these parameters, temperature, volatiles, composition, and melt, influence seismic wave speed, seismic attenuation, and anisotropy. But it also is a case where incorporating data sets from other disciplines, like geochemical and petrological observations or geodynamic models, is important for interpreting along with our seismic images. And then, of course, the oceans represent a substantial gap in seismological coverage, but also a substantial opportunity for scientific progress. So when the Grand Challenge document was published in 2009, at that point there had already been a few receiver function studies that had identified a discontinuity at around 100 kilometers depth that originates from a pretty abrupt decrease in seismic velocity with depth. And in the subsequent 5 years, numerous receiver function studies have really illuminated a global discontinuity in the uppermost mantle that spans a wide variety of geographic and tectonic settings. And in some locations, this boundary or this discontinuity is interpreted to be a boundary within the lithosphere, and in other places it may actually correspond to the rheological lithosphere-asthenosphere boundary. Naturally, most of these observations are on land or ocean islands, owing to the tendency of seismometers to be located on land. But recently, a couple of studies have made use of SS and its precursors to illuminate discontinuities in the uppermost mantle beneath the Pacific. So this has historically been a challenge because underside reflections from a shallow discontinuity arrive pretty close in time to the main SS pulse, making it difficult to distinguish them. I'll show two examples here today, and we've chosen these examples for two reasons. I mean, first of all, they provide valuable new information about the structure of the oceanic plate, but they also, I think, are nice examples of the ways that seismologists continue to extract new and interesting information from waveform data. So Reichert and Scheer have modeled the subtle variations in the characteristics of the SS pulse to resolve a discontinuity in the shallow mantle beneath the Pacific, and the results are summarized in the panel on the bottom left. Here, the circles are the bounce point caps where they've identified this discontinuity, and they're color-coded by the depth of the discontinuity. So they find an age dependence of the depths, with depths close to 25 kilometers near the East Pacific rise, and then more like 130 kilometers beneath older seafloor. And under young seafloor, that discontinuity requires a pretty abrupt velocity decrease with depth. Under normal seafloor, older seafloor, it can be a bit more gradual, and the authors speculate, due to the age dependence, that this may actually correspond to the rheological lithosphere-asthenosphere boundary. Around the same time, Nick Schmer was looking at SS precursors using acceleration seismograms instead of velocity and displacement, which provides access to higher frequencies and a cleaner separation of the precursor from the main SS pulse. And his results are summarized on the bottom right there. The gray squares are stacks in the Pacific where he did not identify a detection of the SS discontinuity in the SS precursors, and then the colored circles show the depths where he did. So there are really two populations at around 55 and 75 kilometers, and a lot of the detections of the discontinuity appear to be near regions of surface volcanism, like near hotspots in the South Pacific superswell and near Hawaii. And so he speculated that these may originate from a layer of melt at the base of the asthenosphere. So recently, Caroline Begin and coworkers have identified an association between the discontinuity of the SS precursors and azimuthal anisotropy in the Pacific. So on the left here, the panels summarize azimuthal anisotropy averaged over the Pacific plate, so old on the left and young on the right. And in the middle panel, they show that the direction of the fast axis of azimuthal anisotropy varies as a function of age and as a function of depth in the Pacific plate. And then if they look at vertical gradients in the direction of azimuthal anisotropy, you can see that they find a peak, a maximum in the gradient at roughly constant depth, 60 or 70 kilometers, and that depth overlaps pretty nicely with the depth where Nick Schmer identified the SS precursors. So this overlaps suggests a possible causative link between the discontinuity and between anisotropy. And then the authors have inferred the rheological lithosphere boundary to lithosphere-asthenosphere boundary to correspond to the depth where the fast axis direction rotates into alignment with absolute plate motion. And you can see in the middle panel there that depth varies as a function of age and roughly follows the 1,000 degree isotherm. So layering within the upper mantle inferred on the basis of vertical gradients of azimuthal anisotropy has also been identified in North America by Ewan and Romanowicz. So they image azimuthal anisotropy using surface waves and using SKS splitting measurements. And the results are summarized in these two cross-sections here. The top cross-section goes from northwest Canada, southeast pretty much to Alabama. And then the bottom cross-section is mostly west to east across the Canadian Shield. And they identify three distinct layers on the basis of the fast axis direction of anisotropy. A top layer with a thickness between 50 to 160 kilometers, where the fast axis is roughly aligned with absolute plate motion. A middle layer, not really aligned with absolute plate motion, and then a bottom layer where the fast axes are again aligned with absolute plate motion, which they infer this layer to be the asthenosphere. So in this scenario, then, the horizon between layers 1 and layers 2 in these cross-sections is a boundary within the lithosphere and may correspond to the mid-lithospheric discontinuity that's observed in the receiver function studies. So like on the previous slide, we've chosen these examples for a couple of reasons. One, they provide significant new information about the structure of oceanic and continental plates. And in the case of the North America study, actually, the thickness and the anisotropy within layer 1 show nice consistency with surface geology, so actually help to provide constraints on the models of continental growth. But these are also two studies that are nice examples of utilizing different types of seismic measurements in a single study. So both studies use the higher mode surface waves in addition to the fundamental modes, and the North America study makes use of SKS splitting measurements. Now, of course, the vast quantities of data that are being collected as part of EarthScope are really helping to illuminate upper mantle dynamics beneath the U.S. And of particular interest are high velocity anomalies in the western U.S., and I'm showing here two examples. So in the top panel, you can see a high velocity anomaly beneath Idaho and beneath eastern Washington that extends from about 230 to 600 kilometers depth. And Schmidt and Humphreys have suggested that this high velocity curtain, as they call it, corresponds to a remnant of the subducted Farallon plate that's been dangling in the mantle for the last 40 or 50 million years. Moving further south, Yun Wang and Don Forsyth and others have suggested that a couple of high velocity anomalies beneath Baja California and also beneath the southwestern U.S. Are fossil slabs that are still attached to their oceanic microplates. So the images here, it's shear velocity at 70 and 100 kilometers depth. So you can see high velocity anomalies associated with the Colorado Plateau, with the transverse range, and then also with the Isabella anomaly. The Isabella anomaly is a feature that's also sometimes called the South Sierra Nevada anomaly and has, by other studies, been interpreted as a lithospheric drip. But in this case, on the basis of both the eastward dip of this feature, which you can see in the cross-section on the far right, and on the basis of its geometry relative to the Monterey microplate located just offshore, these authors prefer an interpretation of a stalled slab. And so these two examples we chose because in part they highlight the way that tomographic images can be used to learn about upper mantle dynamics. So whether or not these high velocity anomalies are stalled slabs or active lithospheric drips has very different implications for the rheology of the lithosphere and for convection within the asthenosphere. But they're also nice examples of the types of small-scale features that we're now able to image with the US array data. And then as our third scientific theme is distinguishing between melt and volatiles, composition and temperature within our seismic images. And this theme is directly related to all of the other examples I've shown so far. So interpreting the tomographic images and interpreting the layering identified from the discontinuities requires a knowledge of how these factors influence seismic velocity and seismic attenuation and also anisotropy. And so to do that, we really need to have close collaboration and good communication with the experimentalists who are collecting this data. But I think perhaps equally important is to perform interpretations wherever possible with data from other disciplines. And so I'll show two examples here. This one is Jeff Abers and a bunch of coworkers actually have recently completed a synthesis of mantle attenuation studies beneath a number of arcs and back arcs. And you can see the results on the panel on the left here. So they have attenuation values beneath Costa Rica, Nicaragua, Laos, and Mariana arcs and back arcs where available. And then on the horizontal axis is temperature, which is actually in this case estimated from the composition of magmas erupted at volcanoes at the arcs. And so they see the expected relationship, higher attenuation at higher temperatures. But then the dashed and solid curves are predictions of experimental data for how temperature should affect attenuation. And you can see that all of the different parameterizations predict lower attenuation that's actually observed. So these observations can't be explained by temperature alone. So the authors then investigated the effect of water on attenuation. And so there aren't many constraints on how water affects attenuation, but it's assumed that it enhances attenuation. But water also enhances grain growth, and larger grains are associated with lower attenuation. So they pretty much found that the effect of the enhanced attenuation is roughly canceled out by the effect of the grain growth, and so water can also not explain the observations. And so that sort of leaves the effect of partial melt in the mantle wedge to explain the high attenuation that they observe. And they're able to show that accounting for melt can bring the predictions pretty much into agreement with the observations. So this is a nice example for a couple of reasons. One, it highlights or underscores the need for better experimental constraints on melt and volatiles. But it also, I think, is a good example of how data from other disciplines can help. So in this case, the fact that they had good temperature constraints from the geochemistry means that they could take temperature out of the equation and just focus on the role of melt and water for these observations. And then as the second example is some work along mid-ocean ridges that I've recently been involved in. We compared mantle shear velocity from S40 RTS with the geochemistry of basalts erupted along the mid-ocean ridge. And you can see from the panel on the top left that we found a correlation between shear velocity at depth in the mantle, in this case 300 kilometers depth, and sodium content of the basalts, with lower velocity associated with lower sodium and higher velocity associated with higher sodium. And we were also able to show that the temperature range estimated from both of these data sets independently agrees pretty nicely. It's a range of 200 to 250 degrees Celsius beneath the ridge. And so doing this sort of analysis, first of all, allowed us to estimate temperature along the mid-ocean ridge, as you can see in the map down there, with the highest temperatures, perhaps not surprisingly, near Iceland, and then also temperature perturbations associated with a number of hotspots near ridges in the South Atlantic. And this allowed us to show that the mid-ocean ridge basalt chemistry is being predominantly affected by temperature and not by variations in composition, but it also provides here an opportunity to understand the points that deviate from this trend. So to look at the scatter about the thermal trend and understand the role of composition and volatiles and other factors in producing those observations. And then finally, I haven't left much time to say much about the oceans, and I suspect that the need for better coverage in the oceans is an idea that's appreciated already by many people in this room. And so I've just put up here, the slide just shows really two potential motivations for an improved effort in the oceans. One is just recognition that from US Array, the results that we've obtained so far challenge many previously held assumptions about continents. So we can only really begin to imagine which of our currently held assumptions about oceans would be challenged by US Array style deployment, say, in the northern Atlantic Ocean. And then also recognizing that a new effort in the oceans would allow us an opportunity to target fundamental concepts that have so far been a bit tricky to unravel in continents and subduction zones. So for example, the relationship between mantle flow and seismic anisotropy, or the details of melt generation and ascension, small-scale convection beneath the plate, and other things like that. So I think I'm at my time, and I'll stop there.